So I'm going to give you two different acids. So in this chapter, a really important part of doing this is to identify the major species. And I'm not just saying like, oh, this guy's name is perchloric acid. Like, yeah, sure. But what kind of acid it is. That's what I mean by identifying the major species. So having said that, identify these two. Tell me what they are. HClO is a what? And HF is a what? Thank you, Micah. Strong acid, weak acid. And the reason that this is important is because we deal with them differently. Now, I need to point something out that tended to confuse kids. So remember the Bronsted-Lowry definition of an acid base is an acid is an electron, or I'm sorry, is a hydrogen ion donor and the base is an acceptor. So I'm going to write the HClO4 equation. So again, the first step, identify major species. Second step, write out the equation or reaction. Now, if all I have is a weak acid, this is not a chemical reaction. This is just the strong acid. You can write it like this. One-way arrow, right, for strong. Or you can write it where you've included water. There is no difference, okay? I realize one has water in it and one does not. But in the grand scheme of things, these two equations are synonymous with one another. This is the acidic hydrogen, this is the acidic hydrogen, okay? There is no difference between these. So what I'm telling you is for the acids, I don't care which way you do it. However, when we go to bases, I do care which way you do it. So pay attention when we get there. Now, I'm not there yet. Now, here's the thing. Remember, we should be getting really good at recognizing pHs and POHs when they're nice numbers. And what I mean by that is this is 0.1 molar. And you go, well, I don't know how to do that. Well, rewrite it in scientific notation. It's 1 times 10 to the negative 1 molar. So what's the pH? Without a calculator, you just look at the exponent, right? It's 1. 1. Okay? And then you go, so the concentration is 1 times 10 to the negative 1. Now the long way is this, pH is opposite log of the hydrogen ion concentration. Or it could be opposite the log of H3O plus. These mean the same thing, okay? So you do opposite the log of 0.1 and you get 1. And the question becomes, why can I do this? Well, I can do this because strong acids are assumed to 100% ionize. So what does that mean? That means that it's not this guy that's in solution. It is this guy and this guy. 0.1 molar hydrogen ion, 0.1 molar ClO4. Or 0.1 molar H3O plus, which is H plus, and 0.10 molar ClO4 minus. Okay? So because it 100% ionizes, off the bat, I know the hydrogen ion concentration and I can solve for pH. This is not true for weak species. You do not know the hydrogen ion concentration based on this because weak species do not fully ionize. That creates an issue and it also creates more work for you. So when you go to, once you identify this is a weak species and you go to write out its equation, you have to write it in equilibrium because weak species go to equilibrium. So it's gonna look different. So one way to do this, equilibrium arrow, H plus F minus. Now this is not a reaction, right? So I'm sorry, I'll do this up here. This is aqueous. Aqueous. Ions are always aqueous, always. When are ions aqueous? Always. And this is a liquid, okay? Aqueous, 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 okay? This is one way to write it. This is like the simplified way. This is like the full version way where you add the water to it. And why do I get to do this? Well, because this is in solution, right? It's aqueous, so there's water present because it's aqueous. And then instead of the H plus, you end up with the H3O plus for the acidic part. But again, they mean the same thing. This guy and this guy are the same thing. They determine the acidity. Now, things that go to equilibrium have equilibrium expressions. Is that right? So how would I write this? K equals products over reactants raised to their respective coefficients. Which one do you do it based off of? I don't care. It doesn't matter. Do it off of this one or this one. I don't care. K equals products over reactants raised to their respective coefficients. Now, I don't include water in there, right? It's a liquid. So if you would have used this top one, it would look identical, except this wouldn't be H3O plus, it would be H plus. Again, it's the same thing, okay? Now, they're going to call this a Ka value, and the reason they're going to call this a Ka value is because this is an acid, all right? Now, to do this problem, if I want to know this guy's pH, again, I'm solving for the same thing. I solve for the pH of the first one. What's the pH of this one? And you go, well, they're the same concentration, so they're the same pH. Wrong. They are not the same pH because they are not the same type of acid. Solving for the pH of the weak acid is more work. Okay? So, what was I going to say? I lost my train of thought. Oh, you need the Ka value for this problem. Like, you would have to either have it be given, or you'd have to look it up in a chart. I think if I remember correctly, the proper one is this. Give me 1 second, guys, please. 1 second. Okay, so let me double check that this is the Ka for acetic acid. It's kind of interesting because different charts show different Ka values. But you don't have to, if you go like Google it, it says 6.6 times 10 to the negative fourth, and I'm telling you right now that that's not the normal one that like the College Board uses. So I'm going to try to find the one that the College Board uses most frequently. Yeah, 3.5 times 10 to the negative fourth, okay? Again, this will be given. You don't have to memorize it. You can't do this problem without it. So like you know this guy, right? Well, things that go to equilibrium, you want to have an ice chart. Why? Because they go to equilibrium. IC equilibrium, right? Now, water's a liquid, so we don't care about it, just like we don't care about it in our expression. This is 0.10. So now this is much different than what we had up here. We didn't even account for our initial concentration of HClO4 because it really doesn't exist in solution at all. Whereas weak acids do. In a weak acid solution, it is like 99% this and only a tiny bit of this. So initially we call these 0. And then now what do? We let X equal the concentration of H3O plus, or you could have picked F minus, okay, at equilibrium. So X. So this is plus X. And what's nice about this one is everything is a 1-to-1 ratio, right? So minus X, 0.10 minus X. And then you take your equilibrium, equilibrium values, and you plug them into your equilibrium expression. So this ends up being, I'll get rid of these. Here we go. So this is X, this is X, this is 0.10 minus X, and then I know Ka, I gave it to you. It have to be given for you to do this problem. So I'm going to plug it in. It's 3.5 times 10 to the negative, oops. All right, And then we do one more thing that helps us avoid the quadratic formula. Assume x is much smaller than the number you're subtracting it from. So in this case, it's 0.1. And that allows us to be like, see you later. Now I don't have to use the quadratic. X times x up top is what? X squared, right? So you multiply both sides by 0.1. Okay. And then you have x squared. So what do? I take the square root of both sides. And x comes out to be, I'll wait for your answers. You would think after doing this 3 times I'd remember, but I don't. Anybody have a number? Does it have a 5 in it, like 0, 5 something? Zero zero 5916. Okay, perfect. So just keep the whole number in your calculator. Whatever, blah, blah, blah. Well, x is my H3O plus, right? That's who I said it was. So this is H plus or H3O plus, whatever you want to call it, or H plus. So now that I know my hydrogen ion concentration, I can find pH, right? pH is opposite the log of H, or H3O plus. So pH is opposite the log of 0.0059, blah, 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 blah. So what does the pH end up being? This one is like 2.23, if I remember correctly. Is that right? 2.23? Awesome. So here's the thing. You have an acid solution and an acid solution. They're both acids. They're the same exact concentration, yet they have different pHs. And the reason for the discrepancy with the pHs is that this guy completely ionizes to give me a really strong acidic pH, where this guy does not completely ionize because it's a weak acid. So yes, it's still an acidic pH, but it is not as strong of a pH as, let's say, 1. Okay? And that's because it is a weak acid. Any questions on this before we move on? All right. So now, instead of an acid, we're going to do a base. So let's talk about bases. So we're going to do the same concentration, okay? 0.1 molar. Someone shout out or text me out one of the strong bases you know. I don't want to do one with an alkaline earth metal. Please don't use family 2. Please use your alkali metals. Any alkali metal one that's a strong base. First one is KOH. Perfect. That's actually what they picked last period. KOH, potassium hydroxide, strong base. So, right, first step, identify major species. Potassium hydroxide, strong base. Okay. And then the other one I'm going to give you is ammonia. And this guy is a weak base. Okay. Now, let's see. Where was I going? Oh, I'm also going to do this. Here is the equilibrium constant for the base of ammonia, 1.76 times 10 to the negative fifth, so it's given. Notice this guy doesn't have a K value because it's not weak. You don't have equilibrium values for things that don't go to equilibrium. So the next step after you identify the major species is you write out the equation or the reaction if there's a chemical reaction. Now, if I just have a base in here, it's just an equation of KOH, 100% ionizing, oopsies, into K plus and OH minus. All right. So the whole thing is that it really isn't 0.1 molar KOH. It's really 0.1 molar K plus and 0.1 molar OH minus. So basically, you know what off the bat? Well, if you know OH, you know POH. So again, remember, this is the same as 1 times 10 to the negative 1. So the POH, because this is OH, is 1. Right? POH is opposite the log of OH, 1, which makes the pH 13, 1.0, 13.0. Okay? So the strong base is easy. You just use the hydroxide, find POH, and then you can find pH. How do I go from POH to pH, or to pH? Remember, POH plus pH is 14. Okay. Not so nice for the weak base. So the weak base goes to equilibrium. Now I'm going to add the water to it because it's aqueous, right? And the reason why this is helpful with bases is it's harder to see what conjugates are formed without having the water here. It's easier with the acids to not have the water. So when you do weak bases, always add the H2O. When you do weak bases, always add the H2O. It'll be easier to see what kind of conjugates are formed. So ammonia, if it's a base, it's a hydrogen ion acceptor. So it turns into NH4+. So if this guy loses a hydrogen, it becomes OH minus. If you have trouble seeing that, right water is HOH. The H goes here, and then the OH is left over. Remember, ions are always aqueous. So, step 1, identify major species. Step 2, write out the equation. Now, this isn't a reaction. This is just an equation for a weak base at equilibrium with its ions. Okay? This is not a chemical reaction. This is just a weak base sitting in a container. Now, if it's at equilibrium, the next step is to write the equilibrium expression. So, K equals products over reactants raised to their respective coefficients. So, I'm going to do it up here, okay? And I'm going to call this a base because ammonia is a base. And there's no coefficients. Everything is 1 to 1 to 1. Notice I don't include water because water is a liquid, and you don't ever include liquids or solids in your equilibrium expression. And now I gave you Kb, and they will give you Kb if it's needed. So I'm going to plug it in because I have a number for it. Okay. So I identified the major species. I wrote out the equation. I don't want to call this a reaction again because it's not a reaction. It's just a weak acid sitting in equilibrium with its ions. I wrote the equilibrium expression because it goes to equilibrium. And then the next thing I want to do is, again, so we were trying to find pH, right? So the pH for this top one is 13. And we're trying to find this guy's pH. That's the whole point. I want to know this guy's pH. So if it goes to equilibrium, an ice chart is helpful. So let's do it. ICE. So this is 0.10. Liquids don't matter. And this is 0 and 0 initially, which is the exact opposite of how we did the strong base. Okay? Now what? When K is given, you almost always have to let X equal, and then we pick one of these guys. Now they're in a 1-to-1 ratio, so it doesn't matter who we pick. I'm going to do hydroxide. Concentration at equilibrium. So this is X. Oops, sorry. E is equilibrium, so this is X. So I must have gained X. Remember, this is your the change row is your stoichiometry, and everything is 1 to 1 to 1. So reactants lose concentration. Now I have all of my equilibrium values. Next step is, sorry about that, is to plug into my equilibrium expression. So the ammonium is X, the hydroxide is X, and the ammonia is 0.10 minus X. And then we get to do this nifty thing where we assume X is much small. X, okay, wow. X is much smaller than 0.1. And that allows me to go bye-bye. Now I don't have to do the quadratic. I'm going to simplify the top because X times X is X squared. And now I solve for X. Multiply both sides by 0.1. Right, that gets rid of that. And then I square root both sides to get rid of the square. And X equals, I don't remember the number. Well, X is who? Is hydroxide, right? So this is my hydroxide concentration. So if I know the hydroxide concentration, I can find POH. So POH is 2.87 or 8-ish. I think it depends on if you keep the whole number in your calculator. So POH is 2.87 or 88 depending. And so you take 14 and you subtract 2.87, you get 11.12. So the pH for the ammonia solution is 11.12. So this is what's interesting is you have both bases, both of these are bases. They are the same exact concentration, yet they're giving us different pHs because they dissociate differently. The stronger base gives us a more basic pH than our weak base. Our weak base is still basic, it's just not as strong of a basic pH as our strong base because it does not ionize as readily. The way that I did it on my answer key is a shortcut method, and when I first teach this to you, I'm not going to teach the shortcut method, mostly because it really frustrates me when kids try to use the shortcut method and then get it wrong because they don't know what they're doing. Here's the thing. When you do a titration and you have an initial and final volume, you need to subtract the two numbers to make them positive. Okay, you don't want a negative number to know the exact volume used. So it's not 0.1, it's not 18.8, it's the difference between them. So 18.7 milliliters of calcium hydroxide were used in this titration. How much HCl was used? It's not 2.5, it's not 16.1, it's the difference between those two. So 16.1 minus 2.5 is 13.6 milliliters. Okay? Now, we need to flash back because they give you volume and molarity for calcium hydroxide. I don't know why my computer is being so awful like this. So they give you this guy. But they're asking you for the concentration, which means molarity of the acid. So in other words, if I give you information about one species, but I want to know about another one, I have to do stoichiometry, mole to mole ratios. And I can't do mole to mole ratios unless I'm in moles. How do you get moles? So we need to flash back, and this needs to come back very quickly. Molarity is defined as moles per liter. Moles divided by liters. Moles divided by liters. How do I get moles? Molarity times what is moles? Molarity times volume is moles. Molarity times volume is moles. Molarity times volume is moles. So the molarity is 0.0100 molar, or moles per liter, times the volume has to be in liters in this instance, 0.0187. This gives me my moles of calcium hydroxide. Ugh, why is it doing this? Well, now that I'm at moles, I can do mole ratios for my balanced reaction. Oh my gosh, stop. So for every 1 mole of calcium hydroxide that react, 2 moles of HCl react. So molarity and volume got me moles. Then I do stoichiometry. So this ends up being 0.0003, what, 52 or something? 374, sorry. Now I have moles of HCl, right? So I did molarity and volume of the base, molarity of the base, volume of the base, and then I multiplied by moles of the acid, right? Okay, molarity, volume, moles of the acid. This N means moles of the acid. It's this coefficient right here. That gives me moles. Well, what's molarity? Moles per liter, right? I know the volume of acid use. It's 13.6 milliliters, which is 0.0136 liters. And you end up with the molarity of, I think it was 0.0275 molar. Now, I know that the bell's going to ring and you can head out if you want to. I'm going to finish recording though. I didn't do it like this on my answer key. So I'm going to finish recording. You guys can head out if you have to. I know some of you have another class. I did not do it like this on my answer key. I did it a little bit differently. So I want to kind of show you what I did, because a lot of kids see this, oh, like molarity, volume, and it looks like the dilution equation. Well, let's talk about what the dilution equation is. So let me get rid of this. The dilution equation looks like this. M1V1, M2V2. And this is great for dilutions, but this isn't a dilution. This is a chemical reaction. So while dilution might be happening, they're actually reacting. And when things react, you have to consider the mole to mole ratios they react in. So what you can do, and this isn't given on the AP test, but you can look at this like an acid-base reaction. So acid, acid, base, base. However, you have to consider their mole ratios, which means you have to plug moles in, and they go on opposite sides. So the moles of the acid goes on the base side, and the moles of the base go on the acid side. And when I say moles, I'm talking about these mole to mole ratios. So this is a 2, and this is a invisible, but it's a 1. Okay? So if you wanted to solve it this way, you could, but you have to consider their mole ratios. And most kids go wrong this way. And this is what we did, though. We did the molarity of the base times the volume of the base, and then we multiplied by the, right, it was molarity volume, and then my my stoichiometry was this. This gave me moles, and then it was a 1:2 ratio, right? I'm solving for molarity of the acid, so I divide both sides by the moles of the base, and then I got moles, and then I divided by the volume of the acid. It's the same thing, right? You're doing the same thing, just in a different order or a different structure. So look, if you want to, in this case, you could keep your stuff in milliliters. So look at, if I want the molarity of the acid, I divide by the moles of the base and the volume of the acid, okay, to get this by itself. So the moles of the base and the volume of the acid all go on the bottom. So molarity is 0.01. Volume is 18.7, and in this case, because it's in both sides, I can use the milliliters. And then the moles of the acid is 2 from this coefficient right here. So the top volume of the acid is 13.6 milliliters. Milliliters cancel. And the moles of the base, there's a 1 in front of here. And you could do it this way, and you would still get the 0.0275 molar.